In the previous class, we discussed the principle of operation of a DC machine. In this one, we will be looking at the construction of the DC machine. So, a DC machine basically consists of two components, a stator and a rotor. Okay, rotor is called as armature and stator provides the field, so stator is known as field winding. Okay, field coils. Okay, so the as I told, the when a current carrying conductor is placed in a magnetic field, it will experience a force. Okay, so here the armature carries the DC current through brush and commutator arrangement. So as I told you in the previous class, a brush is links this commutator with the armature winding. So armature winding is wound on the armature core. As you can see here, we have number of windings, one will be incoming and one will be outgoing. Similarly, we have this pair, number of pairs of winding which is connected to the commutator. Okay, this commutator is linked with the brush which is stationary. Commutator is the rotating part and brush is the stationary part. Okay, carbon brush which links the commutator. This commutator is connected to the windings of the DC machine which will be carrying the DC current. Okay, this arrangement, commutator, this armature arrangement, armature consists of armature core and armature winding, commutator, brush. This arrangement is placed inside this material, this stator. Okay, here which stator has basically these poles at which this windings are wound. These windings are wound as these poles are converted into electromagnets. Okay, when the supply is given to this windings, these poles are converted to electromagnets, and there will be field produced by these poles. Okay, these are field windings wound on the poles of the stator. Okay, so this armature arrangement is placed inside this stator, and it experiences as the current passes through this armature, it will experience a rotating force, and it starts rotating. Okay, so this can be represented in this diagram. As you can see, it is represented in this diagram. So okay, we have this commutator. This is the commutator arrangement. We have this brush here, and we have these windings in the armature. One will be incoming, one will be outgoing. Similarly, we have multiple poles of winding. This winding can be either lap wound or wave wound, which we will be discussing in the next class. So next slide, and this is the yoke of the DC machine, and it also has this pole shoe and field winding which we discussed. Okay, so when the armature arrangement is placed inside the field, a magnetic field, and armature carries a current. Okay, number of armature winding carries a current, it will experience a rotating force which will be the mechanical output. Okay, so as you can see here we have bearings and shaft. This shaft will be connected to the mechanical load. Okay, so similarly, if it's a DC generator, this shaft will be connected to the turbine or a prime mover, and this will start rotating. This will start rotating because it has a magnetic field. And a conductor is being rotated, there will be a rate of change of flux in the magnetic field, and EMF will be induced in these currents. Okay, this EMF will appear across these brushes. This EMF will appear across these brushes, which will be connected to the electrical load in a DC generator. Okay, so this we know, as I told you, that here the both armature and the field are connected to the DC supply. Okay, as the field is electromagnet, instead of using the permanent magnet, we are using electromagnets. An electric coil is wound across the pole, so in order to create an electromagnet. So this armature and field windings can be connected to separate supplies, or can be connected to two supplies in series or in parallel. Okay, if the armature and field windings are connected to separate two supplies. Okay, this is one supply and this is one supply. Field is connected to separate supply. Then that type of motor is referred as separately excited DC motor. Now, if the armature and field are connected in series, if this is connected to this one and these two are connected to a single DC supply, then those type of machines are known as series connected DC machines. Okay, series excited or series DC motors. Okay, if these windings, armature and field windings, are connected in parallel, okay, if this winding is connected here and if this winding is connected here and this is connected to the supply of positive and negative, then those type of DC machines are known as shunt excited DC motor. Then those type of DC motors are known as shunt excited DC motors. So we have separately excited, we have series, and we have shunt. Okay. Similarly, if there are two field windings instead of one, if there are two field windings, if there are two field windings instead of one, and one is connected in series and the other one is connected in parallel, then those type of DC motors are known as compound DC motors. These are the types of DC motors. Based on the application, we will use these many types of DC motors. For example, the series motor has high starting torque. If we require high starting torque, then we will use DC series motor. Okay. Similarly, based on the different applications, the connection of the DC motors will be changed. Okay. So, as I told you, the armature conductors can be connected to the commutator in two types, that is either in parallel or in series. Okay, either in parallel or in series. If an armature conductor is connected in parallel, that means one conductor enters here, current will enter through one conductor and it will be exiting in the next commutator winding, then those type of conductors are known as lap winding. Then we will say that the armature is wounded in lap or lap winding. On the other hand, if all the coils all the coils are connected in series, all the current carrying conductors, if a current is carried in this direction, if all these coils are connected in series, then those type of winding is known as wave winding. It's a series connection. Okay, it only has two parallel paths. As you can see here, this lap winding has the parallel paths equal to the number of poles. Lap winding has parallel path equal to the number of poles. Okay. However, in a series winding or wave winding, the parallel path is only two, one for incoming and one for outgoing. Those many parallel paths will be present in the wave winding. Okay. So these are lap wound and these are wave wound. Okay. So these are the different types of windings in a DC machine. Okay. So this is required in order to solve the problems and in order to understand the back EMF torque generated in a DC machine. Okay. Coming to the back EMF, as I told you in the beginning, so what we are doing is there is a field here, okay, and we are placing a current carrying conductor in this field which will experience a force. But there is also a conductor which is rotating in this magnetic field. There is also a conductor. If you neglect the current in that one, there is also a conductor which is rotating in this field. Okay, because of the current it's rotating, but there is also a conductor which is rotating in this field. Because of the conductor is rotating, there is a rate of change of flux or rate of change of magnetic field on that conductor. So as there is a rate of change of magnetic field, there will be an EMF induced which will be equal to minus n d phi by dt. The induced EMF will be opposite to the source caused. So if it is connected to a source which is allowing the current to flow through the conductor, the induced EMF will oppose this source caused. We know that's because of Lenz's law. Okay, that is what is back EMF. On the other hand, if this back EMF, if it's a generator, then the generator is not connected to the source. Okay, a conductor is simply rotated in the field. Okay, when it is rotated in the field, there will be a current induced. Voltage will be induced on its terminals. That itself will be the back EMF or the induced voltage or the terminal voltage of the DC generator. For example, in a motor we have this back EMF, we have this applied voltage. Applied voltage will be equal to sum of back EMF plus the losses in the DC machine, armature losses, that is IA, RA. Okay, IA, RA losses in the DC machine. Voltage across the armature, the applied voltage will be equal to back EMF plus voltage drop across the armature, which is equal to IA, RA. Okay. In the next lectures, we will be discussing about back EMF and electromagnetic torque generated in the DC machine.